Hello everyone, I'm Musa, a PhD student at Laval University. I want to talk about our new proposed WPT system for implantable medical devices, in which an inductive link bandwidth extended is utilized to realize a robust system. Welcome to my presentation. I organized my speech as you can see here: introduction, problem, elaboration and solution, circuit implementation, in vivo experimental results, performance comparison, conclusion, and question. Wireless power transmission is a traditional technique for supplying the implantable medical devices, which is practical through both inductive and capacitive links. The WPT system charges the IMDs either directly or via an implanted or rechargeable battery. This figure demonstrates the principal elements of a simplified WPT system for delivering power to IMD wirelessly. Consists of a transmitter, TX, and receiver RX boards. The main focus of the recent works on the IMDs are the WPT system operating frequency and the RX board size. In some applications, including optogenetics and miniaturized brain-machine interfaces, the goal of RX design is to have millimeters dimension to minimize tissue damaging. This RX design is powered in the range of microwatt to a few milliwatt. In other applications, the dimension of RX board is around centimeters, where consumes a few hundreds of milliwatt. The amount of delivered power to the implants is in reverse relation with operating frequency. In centimeter-sized devices, FAP is supposed to be in the range of a few to several megahertz to induce sufficient energy to IMDs, whereas the millimeter-sized miniaturized microsystem often operate in the frequency of few hundreds megahertz. In the various application of implants, the inductive links are optimized to result in a promising WPT system. Despite its strong literature, the inductive links suffer from a critical issue that has not been addressed precisely. This issue is inductive link character shifting, which happens due to the loaded parasitic capacitance to the already tuned DX circuit from the implanted side. The value of CAP is different in various tissues, and thus it is difficult to estimate the precise value. Inductive link character shifting results in drastically gain dropping in the operating frequency. For more elaboration, the resonance LC circuit in TX and RX sides are tuned by this equation. In this condition, if the value of L or C being under variation, while the FAP is fixed, the inductive link character will be shifted. The leads wire for a crafted coil chooses to have a proper American wire gauge for providing the best quality factor for TX and RX coils to minimize the losses, resulting in maximizing PTE. In this way, the inductive link is characterized to be super narrow bandwidth. Therefore, even little inductive link character shifting due to undesirable small parasitic capacitance addition in implanted side by tissue surrounded RX board and consequently loaded in external part would lead to a considerable drop in the gain. As a solution, an inductive link bandwidth extended procedure illustrated in this figure is proposed for overcoming to elaborated issue. For implementing this technique, the TX and RX resonance circuits should not be tuned on FFP. The TX and RX circuit must be tuned in frequencies a few percentage lower and higher than FFP respectively. For better clarification, TX and RX resonance circuits should be tuned on FFP minus MFFP and FFP plus MFFP. Beneficial achievements by the proposed inductive link bandwidth extended for WPT system are: compared with conventional WPT systems, it can tolerate inductive link character shifting, resulting in almost the same PTE and PDL with and without not estimated parasitic elements. Addition, due to tissue-surrounded implants, contrary to traditional WPT system, the employed ILBWE for WPT is a robust design. Therefore, it can endure considerable misalignment between TX and RX coils. Third, according to the Shannon-Hartley theorem, channel capacity is in direct relation with bandwidth. So, since the bandwidth of the proposed inductive link is extended, FFP could be changed in the range of the bandwidth. In this way, an FSK signal can be passed through the proposed link in the acceptable frequency range without any disturbance to cover both WPT and send downlink data with a considerable bitrate via the same link. This figure illustrates to clarify how the inductive link bandwidth extended is characterized by network analyzer. The TX port is connected to port 1 by SNA connector, and similarly, the RX port is connected to port 2 to measure the transmission coefficient of the designed ILBWE. The popular frequency of 6.78 MHz for WPT is selected based on the available standards. Consequently, the TX and RX resonance circuits are tuned on 6.68 MHz and 6.88 MHz respectively to extend the inductive link bandwidth appropriately. The RX board is encapsulated to be implanted in the body of anesthetized sheep to prove the concept of WPT with proposed ILBWE. The in-vivo experimental results to prove the concept and test the proposed ILBWE in different conditions, including misalignment test, PDL measurement in different depths of implants, and PT calculation are successfully achieved. The RX board is implanted inside the body. The depth of implants is increased step by step with different surgery by the dedicated medical team. In all the conditions, the PDL and PTE are measured and calculated. In the sixth row of this table, the result of a misalignment test with 45 degree between TX and RX coils is presented. In the seventh and eighth rows of this table, the results of the misalignment test with distance between TX and RX coil are presented. A Class E power amplifier is driving the ILBWE, and 180 ohm resistor is used in the implanted side as the load. This table demonstrates the performance of the proposed WPT compared to recent works. For a fair completion, a figure of merit is presented, which is the multiplication of PTE, FFP, and the square root of RX size divided by 10. In this FOM, the largest one is the best. As a conclusion, we proposed a new method to design an inductive link for wireless power transmission to IMDs. The traditional inductive link were affected by inevitable parasitic capacitance, while in the proposed methodology, the critical issue is solved. The privilege of the proposed link are summarized here. Finally, I would like to thank you for your attention. If you have any question, I am pleased to answer.